So we're continuing our work in Unit 5, applications of derivatives. Specifically, our applications are optimization problems. So we're wanting to find the absolute max or the absolute min on a given domain. And I just want to remind you, we're going on Unit 3. You will be given the function here. This time the function you're going to be given is an exponential function. So in the extreme value algorithm, we do need to know what the function is. And so you will be given f at x. You will have your domain a less than or equal to x, less than or equal to b. And the extreme value algorithm says that the absolute max of this particular function is either going to occur on the endpoints of the domain, a and b, or wherever f prime at c is 0, because that's the location of your local extrema. So the absolute max or the absolute min occur either at the local extrema or at the endpoints of the domain. And I did mention in the previous lesson that in university you will also be worried about where the first derivative does not exist. All right, so continuing forward, we're just going to be doing, I think, 4 examples today. So determine the absolute max and minimum values of this particular function on this domain. So the first thing you're going to need to do is find the derivative of that function. Once you've found the derivative, you're going to test f at 0, f at 3, and wherever f prime at c is 0. So getting to work. Step number 1, take the derivative. And again, you can be in control of the timing. I'm just going to move forward. So the derivative of this would be itself, and then I'm going to have to times by -1. Minus the derivative of that would be itself. And then we have to times by the derivative of the exponent or the baby, which would be -2. Also, the stretch or compression factor is 1 because it's an e to the x function and the ln of e is 1. So that's going to give us negative e to the negative x plus e to the negative 2x. Now I know on the previous day I did examples where we had, I forgot totally what it was. I'm just going to write x to the -2 maybe plus 3600, and we had a negative here. And then I had factored out next to the -2, and then I had suggested to you that if you wanted to find where this was 0, it would also be appropriate to bring that over. In this particular case, it's going to be very difficult for us to try and solve these if we try to apply the method where we bring something to the other side. So it's going to be really important here that we actually become better at factoring out e to the -2x. So that's what we're going to need to do. We're going to factor out e to the -2x. I did note first that we should find where this is 0. So where is 0 equal to that? And then what I'm going to do is factor out e to the -2x. So e to the -2x also factored out the negative so that I would make the term, I would make this a positive exponential function. So we need to do negative e to the negative x divided by negative e to the -2x. Alternately, we can expand and we can see there's negative. Those have the same base. Add the exponents. -2x plus x is -x. A negative times a negative is the positive, and that becomes positive 2 e to the -2x. The other way to find this particular factor is to simply just do a division. We have negative e to the -x, and I'm factoring out negative e to the -2x. Plus 2 e to the -2x divided by negative e to the -2x. And when we do this division, a negative divided by a negative is positive. This becomes e to the -x. Take away -2x becomes plus 2x. You should subtract those exponents. There's our e to the positive x. And those would go, and 2 divided by -1 would be -2. So continuing. This will not be 0. This is an exponential function. It does not have an x intercept. But this piece can be 0. So e to the x minus 2 can be 0. So let's solve that. That has a solution. I'm going to start by bringing the 2 to the other side. Where is 2 equal to e to the x? And now I'm going to undo this by bringing that to the other side. And using advanced functions knowledge, I'm going to get x is equal to ln of 2. So now I have found where the first derivative is equal to 0, so I'm now going to have to check f at 0. We're going to have to do f at ln of 2. And then we're also going to have to do f at 3. So we'll go through these one at a time. So f at 0 would be, well, you plug in 0, the exponent's going to be 0. The exponent here will also be 0. So we'll get e to the 0 minus e to the 0. That's 1 minus 1, and of course 1 minus 1 is 0. Now we're going to do f at ln of 2, but we're going to simplify it because we'll be able to use exponent law, so I'll walk you through that. F at ln of 2 would be e to the negative ln of 2 minus e to the negative 2 ln of 2, but we have an exponent law that would say that negative ln of 2 could be rewritten as ln of 2 to the negative 1. And we have negative 2 ln of 2. There's also an exponent law that says that could be rewritten as ln of 2 to the negative 2. So that's what I'm going to do on the next step. So rewriting this as e to the ln of 2 to the negative 1 minus e to the ln of 2 to the negative 2. And now I'm going to remind you that a to the log base a of b is simply b. So these two have the same base. So the argument for the log function here is going to be the result. A to the log base a of b is b. Just get the argument back. So e to the ln of 2 to the negative 1 is 2 to the negative 1. And e to the ln of 2 to the negative 2 is just 2 to the negative 2. That's 1/2 minus 1/4, which is 1/4. So f at ln of 2 can be simplified nicely down to down to just the value 1/4. I would expect you to be able to show me that particular work on a test. Now we'll do f at 3. That's e to the negative 3 minus e to the negative 6. Clearly that's not a negative value. Your question is that larger than 1/4? So I'm going to factor out e to the negative 6 and get e to the 3 minus 1. It's also possible that you could punch this into your calculator and see what's going to happen. This value is actually going to be between 0 and 1/4. And if we like, we can view this, as 1 over e cubed minus 1 over e to the 6. Now 1 over e cubed is already much smaller than 1/2 because e is, between 2 and 3. So let's take the scenario where it would make it the largest possible number. That would be make the denominator the smallest. So view this as 1 over 2 cubed minus 1 over 2 to the 6. And we can see we now have a value that's positive, but less than 1/4. So the maximum value is going to be 1/4, and the minimum value is going to be 0, because that's less than 1/4. All right, that was our first example. Using exponential functions, let's move on to our second example. This is an example of a logistic function that you possibly looked at in advanced functions, where you have a constant over here, you have 1 plus. You can have another constant times an exponential function to a negative exponent. That's the logistic function, and it ends up tracing out a curve that has an increasing rate of change followed by a decreasing rate of change. So there's our function. The first thing we're asked to do is to find the initial population of pickerel. And my question to you would be, do you need a derivative to do that? Is that a calculus problem, or is that a problem you could have answered in advanced functions? Now I'm just going to move forward, but you can control the timing. This is a question we could have asked you in advanced functions. We really want to know what p at 0 is. So p at 0 is going to be 2,000 over 1 plus 9e to the negative 0.5 times 0. That's just going to become e to the 0. And e to the 0 is 1, and 9 times 1 is 9, plus 1 is 10. So we're 2,000 over 10, and 2,000 over 10 is simply 200. Next part of this question asks you to find the pickerel population after 2 years. And again, is that a calculus question, or is this a question you could have answered in advanced functions? All right, moving forward, that's p at 2. So we don't need calculus for that. That's going to be 2,000 times 1 plus 9e to the negative 0.5 times 2. That's going to become 1 plus 9e to the negative 1, negative 0.52 being negative 1. And now at some point we're just going to have to punch this into our calculator. I'm going to pause for a second. All right, so in my copy and pasting to go from here to here, I left that line in. That line should not be staying there. So you could punch this into your calculator, 2,000 divided by, open up a set of brackets, 1 plus 9 e to the negative 1. You're going to get a number close to 464. All right, neither of those two require calculus. So the next question asks, for the largest population of pickerel this lake can sustain, does this require calculus? And because this is an optimization problem now, it is going to require us to use calculus. The largest value could occur at the endpoints. We know time 0. It didn't give us some time at the other end, but let's just say that was infinity, or anywhere f prime at c is 0. So we're going to have to end up taking the derivative. I'm just going to remind you what the function was. P at t is 2,000 over 1 plus 9 e to the negative 0.5 times t. And now you're going to need to take the derivative. So lots of ways you could do this. I guess we could view this as 2,000 times 1 plus 9 e to the negative 0.5 t. That whole thing to the negative 1. And then kind of use the product rule. There are two terms down here, so we're going to have a hard time avoiding either the product or the quotient rule. I'm going to use the quotient rule. It's possible you could use the product rule if you rewrite it this way, and then use the chain rule. So the 0 here, where's that coming from? Well, I would need to take the derivative of this numerator, and then I would divide it by that. Well, the derivative of a constant is 0, so I don't need to write f prime at g. It's f prime at g minus g at, let me rewrite that. It is f prime at g minus f times g prime. I was starting with the g on the second term, all divided by g squared. Well, I'm pointing out to you that f prime is 0, so I'm not going to write that bit. I just wrote that as 0. 0 minus f, which is 2,000. Now, the derivative of the denominator is going to be, the derivative of the 1 is 0. The derivative of this exponential function is going to be itself, right? So throw that in with the exponential function. It's itself. Its stretch or compression factor is 1. And then I'm multiplying by the derivative of the exponent, which is negative 0.5. So 9 e to the negative 0.5 t times the negative 0.5, all divided by the denominator squared. And then we'll do some cleaning up. We probably could start by multiplying negative 2,009 and negative 0.5. And that gets us to here, which is 9,000 e to the negative 0.5. Half of 2,000 is 1,000 times 9 is 9,000. That takes us to here. Now, we're trying to find where p prime at t is 0. And that would be when the numerator is 0, but it does not appear that that could ever be 0. That's an exponential function, so it should be larger than 0. So since p prime is not 0, because I just mentioned that's an exponential function, and the multiplier is positive, so this is going to be an exponential function. Actually, that's negative, so it's going to be coming down like this, but it is going to be above the x-axis, so it's always going to be greater than 0. So what does that mean? That means we're going to have, there's no place where the first derivative is 0. That means that the largest population is either at the beginning or it's going to be at the end. So we're going to check the endpoints of our domain. So we've already checked p at 0. That was one of the first things we did. P at 0 was 200. And now let's try and think about the other endpoint, which would be the limit as t goes to infinity, because they didn't give us an endpoint, but let's just try and send t to infinity of 2,000 divided by 1 plus 9 e to the negative 0.5 t. So imagine plugging an infinity into that and seeing what's going to happen. So this is going to become 9 over e to the infinity. And of course, that's 9 over infinity, and that's just going to be 0. And we're going to get 1 plus 0. So I'm noting we're going to get 2,000 over 1 plus 0, and that's just going to be 2,000. So the maximum number of fish that this lake can sustain is 2,000. All right, so the next question is asking us the time at which the rate of change is the maximum, i.e. What is the maximum for, so we were using p, right? What's the maximum for p prime at t? So in order to find the maximum for p prime at t, again, it's either the endpoints of the domain or it's wherever p prime at t is 0. So the first thing you're going to have to do is find the second derivative. And backing up a bit, let's just move forward. I pasted over here for you. Let's remind you that that's what the first derivative was. Again, my inclination would be to use the quotient rule on that. So moving forward, again, you can be in control of the timing by pausing when you wish if you'd like to try this on your own. The derivative of the numerator, the derivative of an exponential function is itself. Its stretch or compression factor is going to be 1, and then I'm going to have to multiply by the derivative of the exponent, which is negative 0.5 times t, which is negative 0.5. I then times by the denominator. Minus the numerator times the derivative of the denominator. Well, that is a power of a function, so I'm going to start with the outer function. The 2 comes down, 1 plus 9e to the negative 0.5t to the power 1. And then I'm going to have to then multiply by the derivative of the baby function, or the inner function. The derivative of 1 is 0. The derivative of this exponential function is itself, times its stretch or compression factor, which is 1, times the derivative of the exponent, which is negative 0.5. So that gets me to there. So this little bit here, f prime, that's g. Here is f. And from there to the very end is g prime. So now we're going to have to clean this up a bit. So what can we do? We can factor out 9,000 out of each of these, right? We can factor, just underline, we can factor out 9,000 can come out, negative 0.5 can come out. E to the negative 0.5t can come out, e to the negative 0.5t can come out, and then 1 plus 9e to the negative 0.5t. So we can factor all of those pieces out. So on the next slide, I have factored out 9,000 times negative 0.5, but that's negative 4,500, so I just wrote that as negative 4,500. Then I said e to the negative 0.5 could come out, and then we could also factor out 1 plus 9e to the negative 0.5t. So just showing you that it works. If we expand, we now have this times this. That gives us this piece right here. Now, negative 4,500 times 1 gives us that times that, and the e to the negative 0.5t gives us that. So we've got the first term taken care of. Now, if we're going to take a look at the next piece, so let's do negative 4,500. I'm not sure what I'm writing there. Okay, I had inadvertently not deleted an extra 9 that was there. That should not have been there, so I've taken that out. I already explained this. I didn't see that 9 initially. I explained why the first little bit worked. Now let's check the second little bit. So negative 4,500 times negative 2, that's going to give us positive 9,000, right? And so we've got our positive 9,000 sitting there. Or we can take a look at, and there's the extra 2 sitting there. So if we do this, times that, negative 9,000. Negative 9,000 times 2 times a negative 0.5. All of those are going to give us the same value as here. So positive 9,000, that times that, so let's underline that, times that, times that, gives us our positive 9,000. Now we need this little piece. That can come from here. Now we need this little piece. I didn't factor that out of there. I factored it out of here. There's e to the negative 0.5. That's that piece there. And then the piece that's remaining is sitting right there. And so now we can clean this up. We've got 1 plus 9 e to the negative 0.5t. Looks like minus 18 e to the negative 0.5t. And so when you do 1 plus 9 e to the negative 0.5t minus 18 e to the negative 0.5t, because I left some steps out here. Those give you negative 9 e to the negative 0.5t. So that takes me up to there. The other thing I can do as well is if we take this function squared and we square it, we're going to get 2 times 2, which is 4. So the exponent is 4. I can then divide this piece by this piece and reduce this exponent to 3. So that's going to leave me with negative 4,500 e to the negative 0.5t times 1 minus 9 e to the negative 0.5t, all divided by 1 plus 9 e to the negative 0.5t cubed. There's my final simplified form. And then I just need to figure out when the numerator is 0, because I want to know when the second derivative is 0. So the second derivative will be 0. That can't be 0. That's actually going to be less than 0, because this is an exponential function. The thing out in front is negative, so it's been reflected down. It's an exponential function that should look like that because of the negative there. But because of the negative out in front, it's going to be flipped this way. So it's going to be less than 0. So we're going to need to solve for when that second factor is equal to 0. So when is 1 minus 9 e to the negative 0.5t equal to 0? We can bring that to the other side. So when is 9 e to the negative 0.5t equal to 1? Bring this to the other side by division. It'd be 1/9, but I'm going to write that as 9 to the negative 1. So when is e to the negative 0.5t equal to 9 to the negative 1? This can come over to the other side on a ln, so we'll do ln of 9 to the negative 1. So we're left with negative 0.5t equals ln of 9 to the negative 1, divide to bring that over, and we're now at t equals negative 2. If you divide by negative 0.5, write that out in front, division by negative 0.5 is the same thing as multiplying by negative 2. Or alternately, imagine just multiplying both sides by negative 2. And then what you will have over here is negative 1/2 times negative 2 is positive 1. We now have negative 2, 9 to the negative 1. But there is a law of logarithms that allows me to bring that inside there. And when I do that, I'm going to get 9 to the negative 1, all to the negative 2. The power of a power, you should multiply those exponents. It's going to give me 9 squared. So that becomes ln of 9 squared. That becomes ln of 81, and ln of 81 is around 4.4. So the rate of change will be a maximum at 4.4 years, and I did mention when we first started what the initial population was, 200. Then we're going to get an increasing rate of change followed by a decreasing rate of change. This is flattening out at 2,000, right? We've got a horizontal asymptote. I want to move that over a little bit. Stretch that up. Move that back over. So we've got that horizontal asymptote right at 2,000. And so we're hitting this maximum rate of change when the tangent slope is the steepest. That's right there at that point of inflection where we're going to change from concave up to concave down, and that's at approximately 4.4 years. All right, so that's the end of that particular lesson. Or not particular lesson, sorry, that particular question. Let's move on to the next one. So the net monthly profit from a sale of a certain product is given by this particular function here. X being the number of items sold. This is the profit in dollars. Find the number of items that yields the maximum profit. At full capacity, the factory can produce 2,000 items per month. So that's giving us our maximum value. So X is less than or equal to 2,000. And maybe we'll make our low end 0, but clearly the company should probably produce something more than 0 if they want to make a profit whatsoever. So the first thing you're going to need to do is find the derivative. All right, so finding the derivative, there's the constant. I'm going to leave that out in front. Now the derivative of 1 is 0 plus, I'm going to have to use the product rule on this. So the derivative of x minus 1 is 1 times e to the negative 0.001x goes there. So that's f prime times g plus there's f times the derivative of g. Now, the derivative of an exponential function is itself, so there's itself. Its stretch or compression factor is 1, so I didn't bother to write it, and that's the derivative of its exponent. And then we're going to try and have to clean this up, right? The 0 goes, that's an e to the negative 0.001x. Then I can expand that little bit there. So actually, I didn't expand. I decided that it was going to be easier to just factor this out of both pieces. That's true, it would work. So 10 to the 6 e to the negative 0.001x, and what's that going to leave me with? A 1 from here, minus 0.01 from there, times the x minus 1 from there. And then moving forward, now I'm going to expand. That's 1 minus 0.001x plus 0.001. We can now add those two together. And I'm going to get 1.001 minus 0.001x. Now this is an exponential function. Its multiplier out in front is positive, so it's going to look like this. The bottom line is it's greater than 0. So now we're going to have to solve when that piece is 0. So when is that 0? So p prime at x is going to be 0 when this little bit here is 0. So 1.01 equals negative 0.001x. First thing we'll do is bring that to the other side. And then after I do that, I would then divide. So just in case someone needs to see this step, equals 0.001x. So 1.001 equals 0.001x. I would now divide by 0.001. Divide by 0.001. And punching that into your calculator, you will get 1001. So now what? So now we need to check p at 0. Then we're going to check p at 1001. Then we're going to check p at 2000. And according to Eva, whichever of these three is the greatest, that will be our maximum value. So let's get started. Plugging in, well, I'm just reminding you that's where we're plugging into. P at x is 1 plus x minus 1 e to the negative 0.001. You do have to plug into here. Some students make the mistake of plugging into the first derivative. You plug into the original function. So p at 0 is 10 to the 6 times 1 plus 0 minus 1 e to the 0. E to the 0 is 1. 1 times negative 1 is negative 1. 1 plus negative 1 is 0. So 0 times that is 0. So not surprising. If you don't make anything, you don't make a profit. We shouldn't be surprised by that. Let's check 1001. So we are going to be, let me pause for a sec. All right, so a bit of a typo. We are checking 1001. So it's 1 plus 1001 minus 1 e to the negative 0.01 times 1001. If you punch all of that in and around, you're going to get 3.67 times 10 to the 8. Now we need to check p at 2000. So that would be 10 to the 6, 1 plus 2000 minus 1 in brackets times e to the negative 0.01 times 2000. Punching all of that into your calculator or Desmos will give you 2.72 times 10 to the 8. So we now can see that the company is maximizing its profit right there when it produces 1001 items. And that's when its profit is going to be. All right, I believe one last question to go. A rumor spreading through the population in such a way that T hours after it began, the percentage of people involved is given by this function. What's the highest percentage? That's how we know we're optimizing. It's asking us for the highest percentage involved in spreading the rumor within the first 3 hours. So that, of course, is giving us our domain. So 0 is less than or equal to t, which is less than or equal to 3. The next thing we're going to need to do is we're going to have to find p prime at t, so we can find when p prime at t would be 0. So you can now take the derivative of this. Again, you're in control of the timing. Pause if you'd like more time to think. I'm going to move forward. P prime at t is 100. The derivative of e to the negative t is e to the negative t times negative 1. The derivative of negative e to the negative 4t is going to be negative e to the negative 4t times negative 4. This gives us negative e to the negative t. This gives us plus 4 e to the negative 4t. And now in order to figure out where this is 0, what we're going to do now is factor out the lowest exponent. That would be negative 4t. So we'll factor out e to the negative 4t. When we do that, when we divide e to the negative t by e to the negative 4t, we will get negative t. This will become e to the negative t plus 4t. And that gives us e to the 3t. So that's what we're trying to do. We want these exponents to become positive. So this is negative e to the 3t. When we factor that out of here, that's gone. So we're just left with plus 4. And now we're going to need to find when this is 0. This little piece here is greater than 0 because it's an exponential function with a positive coefficient out in front. It does have a decreasing rate of change though, but it's greater than 0. So now I'm going to have to solve when this piece is 0. The second factor can be 0. So when is 0 equal to negative e to the 3t plus 4? First thing we're going to do is bring that over. So we now have 4 is equal to e to the 3t. Then what we're going to do is undo this by taking the ln of 4, and that should be equal to 3t. So ln of 4 is equal to 3t. We will then divide by 3. So t is now going to be equal to ln of 4 over 3. And just because I knew I was going to have to plug back into there, I would prefer, instead of seeing this as 1/3 times ln of 4, I'm going to use exponent laws to bring that, not exponent laws, laws of logarithms to make the multiplier out in front an exponent. So this is ln of 4 to the 1/3. So now what? Now we have to check p at 0, p at 1/3 ln, actually let's do it this way, p at the ln of 4 to the 1/3, because that's the friendliest way to plug into that. And let's make sure that looks like a third. And then we're also going to be checking p at 3. So let's get started. So the original function, just to remind you, p at t is 100 times e to the negative t minus e to the negative 4t, plugging in a p at 0. That's going to be 100, that's e to the 0 minus e to the 0. 1 minus 1 is 0 times 100 is 0. So p at 0 is 0. Not surprising, because when we begin, really nobody's involved in passing on the rumor yet. So let's try p at the ln of 4 to the 1/3. That's going to be 100 e to the negative ln of 4 to the 1/3 minus 4 ln of 4 to the 1/3. Now that can move to the exponent, and that can move as an exponent. We're going to have powers of powers. So we're going to have ln of 4, and this is going to become 4 to the 1/3 to the negative 1. And of course, power of a power, you should multiply those exponents. That's going to be 4 to the negative 1/3. The other one is going to become 4 to the 1/3, all to the negative 4. We've got a ln in front of that. So that's going to become ln of 4 to the negative 4/3. So ln of 4 to the negative 1/3, ln of 4 to the negative 4/3 after we pull these back in. Now why did we do that? We did that because this is just going to be 4 to the negative 1/3, and this is just going to be 4 to the negative 4/3. Again, a to the log base a of b is b. So that takes us there, 4 to the negative 1/3 minus 4 to the negative 4/3. I'm going to imagine that what I did next is factor that out. Let's just see if I did. 4 to the negative 4/3, that gives me 4 minus 1, and again, hopefully we're getting better at this. 4 to the negative 1/3 divided by 4 to the negative 4/3. You're going to get 1 negative 1/3 plus 4/3. And that's going to give you 3/3, which is 1. So that's why that's become 4 to the power 1. Alternately, multiply these together. Negative 4/3 plus 1, which is 3/3. Negative 4/3 plus 3/3 is negative 1/3. And of course, there is your minus 4 to the negative 4/3 when you multiply by 1. That's going to give us a 3 there. So we're now going to be 3 times 4 to the negative 4/3. Then after that, this is my exact value, and I'm practicing exact values just in case you need them for university. That's approximately 47.24. I can clearly tell that this value is greater than 0. I wasn't so sure how readily I'd be able to tell whether it was greater than the value I plug in when I get 3. So let's plug in the 3. P at 3 is 100, e to the negative 3 minus e to the negative 12. And what? That's e to the negative 12, e to the 9 minus 1. I'm still going to have to punch that into my calculator so I know what that is. And that's 4.9 or 4.98. So I can now see that this particular one was the highest value. So the greatest percentage of people involved in spreading the rumor was 47.25, and it occurred at ln of 4 to the 1/3 hours, which is approximately 0.46 hours. All right, so that brings us to the end of lesson 3, and lesson 3 was really continuing what we did with lesson 1, which was using EVA. So continuing using the extreme value algorithm, but with functions that all involved exponential. Well, I guess we were saying, maybe I'll reword that, using exponential functions or using functions that were exponential. If you've made it to the end of this lesson, stay tuned for lesson 4. The big difference in lesson 4 is going to be, I'm not going to give you this. We've practiced EVA for 2 days, and we're not going to be practicing EVA any longer. We're going to be figuring out how to come up with these equations. So once again, thank you for watching, and as always, take care.